Alright, so for the post-lab notes, you should have gone through and evaluated what you saw for relationships with these first three graphs on the front page, surface area, material type, and velocity. And then on the back page, this is where we're going to start, you have your frictional force and normal force and how those two relate. As you see on this graph, we have that nice line with a positive slope. So this does tell us, as I increase my normal force, my frictional force also increases. And there's a correlation very close to 1, which tells us that they're highly related or correlated. And therefore our error on this, talking about how far apart those dots are from being on that line of best fit, is very small. So we do have a relationship between normal force and frictional force. The type, since as one increases, the other increases, and it's a nice straight line or linear, that is our direct relationship. Our mathematical model that we're trying to find is going to be to fill in that y equals mx plus b. Instead of y, we have our frictional force, so we're just going to label that FF is equal to our slope, which we have here, is 0.476. Newtons over newtons as our unit cancel with each other, so there is no unit on that slope. And then x is not x, but our normal force, so Fn. Our intercept is plus, we have negative 0.117 newtons. That's so close to 0, and if we kind of think of that thought experiment with 0 normal force, the surface is exerting no force on an object, there shouldn't be any friction because those two surfaces therefore aren't in contact. So we're going to kind of ignore that intercept, and this is our mathematical model. But what does this all mean? What does that number tell us? In the lab, you would have seen a different number for perhaps the duct tape on the table, or the duct tape on the wood, or the felt on the duct tape. But you still would have found a relationship for that specific surface material with the table or with whatever else you were testing it on. This tells us this number is some type of relationship. It shows us a constant, and this constant is a known value, meaning it doesn't change, for the surfaces being discussed, right, for what you did your lab on, and this constant is called the coefficient of friction, abbreviated by mu, the Greek letter mu. The coefficient of friction depends on the nature of the two surfaces, aka what it's made of. So steel on steel has a different coefficient of friction than aluminum on steel. It really just depends on those two surfaces being talked about. Also, the value of friction is different for static and kinetic, as seen in our pre-lab, where we looked at that graph. You have static friction right here while it's stationary, and then kinetic friction. So there has to be a different value for the two coefficients. So in static situations, you'll see mu sub s for static, and kinetic, you'll see mu sub k for kinetic while it's moving. So whether or not your problem tells you it's moving, use your kinetic, or static for stationary. And this table can be found or looked up, or it should be given to you as that coefficient. So finding out what this number meant, this slope for that means, this coefficient of friction, therefore we can write our final equation with all variables to relate the frictional force, and that slope is our coefficient of friction, or mu, times our normal force. So this being our normal force, coefficient of friction, and frictional force. If you have those three, or two of those three values, you can solve for the other one. So let's take a look at Lola on the bottom. She's dragging her teddy bear across a wooden floor with a tension force of 7 newtons at an angle of 40 degrees from the horizontal. The teddy bear has a mass of 1.5 kilograms and a weight of 14.7 newtons. Solve for the acceleration. So it's probably a good idea to start with a force diagram. We have our force of gravity down, our frictional force, she's moving, so kinetic friction to the right, she's moving to the left. Normal force on the teddy bear by the surface, straight up or perpendicular. And then we see this tension force at an angle of 40 degrees, which also tells us we need those components in there. So this would be Ftx and Fty. It's asking for acceleration, and we know that we can find acceleration with our kinematic equations or with Newton's second law. So F equals ma, or net force equals mass times acceleration. We need our net force to solve for that one. Since we don't have our net force, we need a way to find it. We're always looking in the direction of acceleration. The teddy bear is not accelerating up or down, but it's to the left and right, or horizontally, so net force in the x direction is which way we're looking at. We can write our net force equation for the x direction to find that net force. Ftx plus Ffk. And then we run into another problem. We don't have the frictional force, and we don't have the tension force or that component. So looking for that frictional force, we have our new equation up here. So Ff, and this could be k, equals mu k times Fn to solve for that frictional force. This tells us we need to find our normal force. In order to find our normal force, you have to be able to find your net force equation in the vertical direction, because our normal force is not equal to our force of gravity in this scenario. So we have our net force in the y direction equals Fg plus Fn plus Fty. It's not accelerating in the y direction, so we know our net force is 0. Fg was given to us as 14.7 newtons, which is down, so it's negative. We are looking for Fn, and we have to solve for Fty. So to solve for Fty, we want to do some trigonometry. We have our tension force at that angle, Fty, Ftx, and Ft at 40 degrees. So Fty is opposite of our angle, so sine of 40 degrees is equal to Fty over our tension force, which was given to us as 7 newtons. That value for Fty is equal to 4.5 newtons. So we can plug that in up here, 4.5 newtons. Solve to the other side for Fn, so add 14.7, subtract 4.5, and then you get a value of 10.2 newtons for Fn. So now we can plug that in over here and solve for the frictional force. The frictional force we're looking for, mu, we have to find mu kinetic, or the kinetic coefficient of friction, we have to find for the two surfaces. So looking at the table, you see above, you see steel on steel, aluminum on steel, and then you come all the way down and you see teddy fur on wood. So since Sheila is being a teddy bear, is being dragged across a wooden floor, we need to use that kinetic coefficient of friction. So that's 0.30 times our normal force of 10.2, and that frictional force is equal to 3.06 newtons. This can now go into our net force equation, but we do have one other piece missing. We don't have our force of tension that's acting in the x direction. So we have to use trigonometry to find that as well. So we can come back to our triangle down here. We're looking for the adjacent side, so that would be cosine of 40 degrees is equal to ftx over 7 newtons. And that value is 5.36 newtons. So this can also get plugged in over here. So now we have net force in the x direction that we're looking for is equal to 5.36, and since ftx is in the negative direction, we add a negative sign to that. Our friction is 3.06. Net force in the x direction is then equal to negative 2.3 newtons. This value can now be plugged in for our net force right there in Newton's second law, and then we have to plug in for our mass. So net force is negative 2.3 newtons. Our mass was given as 1.5 kilograms times our acceleration. Divide over on both sides by 1.5, and you get your acceleration to be 1.53 meters per second squared. So quite a bit of work to get down to just acceleration, but this is trying to stress that the normal force is what's causing that frictional force to have a value, or that certain value, not the force of gravity. So as she's pulling up into the left, that up part of her pull decreases the normal force with the teddy bear and the floor. So therefore the friction felt between the teddy bear and the floor is less than as if it was just sitting there. So a couple steps to get there, but you still have all the pieces that you've been using in the past. All right, enjoy.